All right, number 14. This is our last and most complicated of our calculations of a titration. And the reason this is going to be complicated is if you look at 13 first, in 13, every time we have a strong acid and strong base react, we get a salt, and that salt has no effect on the pH, because the salt of a strong acid and strong base is neutral in water. However, here, when we're reacting a strong base with a weak acid, we're going to end up with some weak acid remaining and some salt of the weak acid, the conjugate base. And so it's going to form a buffer when we're in the middle of the titration. So we're going to do 5 calculations and 3 types of calculations. A is going to be just having a concentration of a weak acid. The 3 calculations in the middle, B, C, and D, will be buffer type calculations. And then E is going to be a calculation of a concentration of a weak base, because at that point we've converted all of the weak acid to the conjugate base, and that conjugate base will affect the pH of the solution. So let's get started from there. All right, so at the beginning of the titration, we have 100 milliliters. I'm going to divide it by 1,000 in order to make it into liters, so that I can just straight away multiply it by the molarity and figure out how many moles of that benzoic acid I have. Okay, 0.0100 moles. C6H5COOH. You guys don't need to know the formula, but I'll put it there. So that's how much we're going to start out with. For A, we're given the concentration and the Ka. That's actually all we need in order to figure out that first pH. So first, let's make sure that the shortcut works. Ca divided by Ka is equal to 0.100 divided by 6.5 times 10 to the minus 5. Okay, that's about 1,500, which is definitely much larger than 100. Therefore, we can use the shortcut. H3O plus is equal to the concentration Ca times Ka. .54, yeah, 55 really, 2.55 times 10 to the minus 3. pH equals minus log H3O plus minus log H3O plus. So right now 2.59 is the pH of the benzoic acid solution before we've added any base to it. All right, now let's dive into the middle here and do these buffer calculations. So we start out 0.0100 moles of the benzoic acid. And we're going to react that in this first one with 25 mLs, or 0.025 liters of a 0.100 molar potassium hydroxide solution. .0025 moles of KOH. Okay, so here's where the weird part of this comes in, because as I had said at the beginning, this self-buffers, and so what happens is the first part's going to look like something you've seen before. Okay, 0.0100 0.0075 moles of the acid. Okay, so we destroyed 25% of the acid. But in doing that, we didn't make a salt. We make a salt that affects the pH. So we have turned that into the conjugate base. So this is acidic and that's basic. Okay? This one's acidic and that one's basic. And so we're going to have to calculate the concentration of the acid and base and then use the Henderson-Hasselbalch equation. So concentration of the base our total volume right now is 125 milliliters or 0.125 liters. Okay, 0.02 molar for the base. .06 molar for the acid. And now pH is equal to pKa, and our Ka, we need to do that. Let's do that over here. pKa is equal to minus log of our Ka. Okay, 4.19. Put in my pKa value, base over acid. So base on top, 0.02 over 0.06. Minus 0.48. 3.70 for our pH at that point. All right, we'll continue on to C. Okay, moles of the acid. Moles of the base. Zero 0.005 moles of the acid are hanging around at the end of that. And the other half has been converted to the conjugate base. Let's divide these by the total volume in liters. We're up to 150. 0.150. 0.033, same concentration, 0.033. Okay, so pH equals pKa plus log. So acid, be easy to see, equals, worked this out a second ago, 4.19 plus log. Those are the same for this problem, so log of 1, that might be something special. Yep, that's 0. So 4.19 is our pH at that point, when we've got exactly half of the acid neutralized. Part D. I've done it a few times, so I didn't bother actually putting the calculation in. We're up to 0.0075 moles. At this point, there's not much of the acid left. 25% left. 75% of it's been converted to the conjugate base. Our volume is up to 175. Okay, you may notice this is exactly 3 times more concentrated than that, which makes sense. pH equals pKa plus log, which one's the base? This one. .67. Okay, pH is increasing as we go along. Final one, 15E. Okay, this one's different than the strong acid, strong base case overall. So what's similar is they react, and this guy gets completely destroyed. The strong base completely reacts with all of the weak acid. So we're left with 0 moles of the acid. But we're left with some concentration here of the base. Our volume now is up to 200 mLs. 0.1 divided by 0.2, so 0.5 molar C6H5COO minus. Well, what have we got now? We know that we have 0.05 molar C6H5COO minus. So now you're just to the type of problem like you would have worked earlier, a simpler problem where I've told you just the concentration and the concentration of the acid. But we need one more thing. We need a Kb. What do we have in hand though? We have the Ka for the acid. Ka for the acid, 6.5 times 10 to the minus 5. Kb is Kw divided by the Ka. Okay, 1.54 times 10 to the minus 10. That's our KB. Okay, so CB times KB. Okay, you guys are experts at this type of problem by now. We're going to see if the shortcut will work. Concentration is 0.5, and divide that by 1.54 times 10 to the minus 10. Okay, huge number. Much greater than 100, so this definitely will work. Concentration of hydroxide is equal to CB times KB. Okay, 8.77 times 10 to the minus 6 molar. I'm going to do POH. POH is equal to 5.06. So pH would be equal to 14 minus 5.06. 8.94.